Well, it's a pleasure to welcome you and to open the workshop of the missing person arrives. And since this is not completely endogamic, I will say a few words for the new faces. So this workshop is organized in the framework of a research team in philosophy of mathematical physics, which is financed by a grant of the European Research Council, and which is hosted by the Institute Sphere, which means Science, Philosophy, History, which depends on both the CNRS and this university. So first of all, I thank all these institutions for making this happen. And secondly, I wanted to say something about what we do. Let's say that our activities are based on a particular methodological decision, which is to try to unpack conceptual analysis of physical theories by adopting a particular methodology, which is to consider the theories from the viewpoint provided by, let's say, new mathematical formalisms or new mathematical viewpoints on these theories. So instead of addressing these theories by using the mathematical formulation, which is the usual one used by the working physicist, we try to make a shift and to use either new non-standard mathematical formulations of the theories in question or new formalism that might be pertinent for some reason. And in particular, we work on quantum mechanics and classical and quantum gauge theories. So that said, let me introduce Mathieu Anel. He's a mathematician coming from algebraic geometry, if that is correct. And
yes, yeah.
And so
it's unclear.
We are really very lucky because he's currently working with us, and so he will speak about ambiguity in mathematics. That's right.
Yes. Thank you, Gabriel. Thank you for being here.
Just one.
Sure.
This is a very small workshop, but there was some kind of organizational activities which were non-trivial. So I also would like to thank the people of the team, like Federico, Christine, and Julian, who make this happen also. I'm sorry.
I was about to say. Okay, so here is the title of my talk. Stupid. So I'm going to talk about the problem of identification of two mathematical objects and how this identification leads to ambiguity problem. And precisely the motto is, or one of the slogans will be that the non-canonicalities no.
Could you write bigger?
Oh, sure, sorry. Is there a brush? Yeah. So one of the slogans of the talk would be that the lack of canonical identification between two mathematical objects provides an ambiguity. So I'll come back to this at length. And one of the positions that I would like to emphasize is that ambiguity is well encoded mathematically by groupoids. So I'm going to start the talk by giving some examples, and then I'm going to elaborate a position on those examples. So let me give you first a first list of examples. I'll give more later. to explain what I mean by identification of objects in mathematical settings. So probably the simplest situation of identification is that of construction of quotients. Quotients of sets, vector spaces, manifolds. Another situation is when we are trying to compare an object to itself. So that's the problem of symmetries. A related problem is the comparison of two different objects. And let me give you a last example. That would be the description of the change of position of an object in some space. So mathematics have invented several notions to deal with those problems. So let me give you, maybe I can write in a different form. So to deal with quotients, we have the notion of an equivalence relation. To deal with symmetries, we have the mathematical notion of a group. To compare two different objects, this is the notion of a tensor. And if I want to study the movement of a groupoid in space, this is the example that I choose to introduce the notion of groupoids, and I have in mind the use of groupoids that is made in Klein geometries. So it turns out that the notion of groupoids encompasses all the other notions. So maybe oof. So let me explain briefly the definition of a groupoid. So I won't give a formal definition. I will just give a kind of intuition. So a groupoid has two kind of things: objects and arrows, and it can be pictured. So we can picture the objects like this, and I'm going to picture the arrows by actual arrows. And for those who knows that a groupoid can be defined as a category with invertible, oh sorry, maybe that's too small. Okay, sorry, this one doesn't work. A groupoid can be defined shortly as a category with invertible arrows. It means that I can go both direction on the arrows and I can compose the arrows. For example, here in this picture, I'm missing an arrow here that will provide a composition for this. My picture is kind of incomplete because I can have a lot of arrows between two objects, and I can have also arrows going from one object to the other. So let me give you a bunch of examples of groupoids that I hope will explain the notion better than the definition. First of all, an equivalence relation is a groupoid. So if I have an equivalence relation on the set E, the object will be defined as being E and the arrows as the set R. A group is a groupoid with one single object. So in the term of those pictures, an equivalence relation will have a unique arrows between two objects, or no arrows between objects. And a group would look like something having only a single object. So a torsor is a groupoid with two objects. And if you don't know what is a torsor, because this is not such a classical notion, you can take this as a definition. So this is the way I picture a torsor. It has two objects. The objects have a group of symmetries, and between those two objects I have a lot of isomorphism. So the situation for a torsor is to have two objects A and B. Between them I have the set of isomorphism between A and B, and for each A and B I have the automorphism of B here and the automorphism of A. Both groups are acting on this set by composition, and this is essentially the definition of a torsor. Okay. So more example. So just a remark, the notion of torsor is probably, it may be the most important in what I want to say today. Even though this is not a notion that is very much emphasized in the literature. Anyway, but I guess that's a philosophical opinion. So more example of groupoids. If I have a family of objects, then I can define the groupoid of symmetries of this family. So the objects are the sets indexing my family, and the arrows between I and J are the isomorphism between the two objects EI and IJ. So this is the definition of the group of automorphism of a single object. If I have a family of objects, I don't get a group of automorphism, I have a groupoid of automorphism of the family. If a group is acting on a set, I can build a groupoid, which is called the action groupoid. So I'm sorry, I'm just mentioning it without giving any more details. And probably the most famous example is the fundamental groupoid of a topological space. The objects are points of X, and the arrows are path in X up to homotopy. So let me say something about the definition of a groupoid. Essentially, the definition of a groupoid has three axioms. And one axiom says that, which can be understood as a generalization of the axiom of an equivalence relation. So for every object, I need to have an identity arrow. Every arrow going from one object to another needs to have an inverse going the other way. And the most fundamental data is the composition of arrows. So here in this example, this is the composition of path, and this is why we need to work up to homotopy, so that this composition is an associative structure. So, where is the ambiguity in all those examples? Essentially, in my opinion, it's essentially in the notion of torso. Meaning it's the fact that two objects are usually not canonically identified. Sorry, of course, for two objects, it's obvious, but I want to take two isomorphic objects. So in the example of path, if I want to identify 2 points in a space, well, depending on the space I'm in, I can have different paths to choose to identify the points. So the consideration, instead of having the identification of two objects as a property, which would be exactly what is doing the notion of an equivalence relation, the notion of groupoids describe identification as a structure. Meaning between two objects, not only I know that there is an identification, but I have a full set of identification. So I keep track of all possible choices. And keeping track of choices is the way to get rid of the ambiguity. If I have a situation where I have to make choices, this is precisely what I call an ambiguity situation. And the only way to get rid of the problem and to have canonical construction is to keep track of all possible choices. So let me continue an example. When did we start? Gabriel, do you remember when we started? Marca? Okay, thanks. So now I would like to illustrate that in the practice of mathematics, we often have those choices appearing, and if we want to deal with an object as simple as a group, for example, we will need a presentation of this group, and this presentation is a choice, and there's many presentations that I can do, and some construction on the group depends on the presentation. And so I'm going to give examples of situations where somehow the actual manipulation of objects goes a bit beyond the object itself. So I've made a kind of classification of situations, and so I'm going to try to make a table here. So there's the situation where we have more than we need. So this is, for example, the notion of modules, which can be constructed from system of linear equations, and somehow there's more in the system of linear equations than just the module of solution of these equations. More generally, we have any kind of algebraic structure, and we have generators and relation for such a structure, and there's more in the generators and relation than in actual structure. We have manifolds for which we have atlases, and they play the same role. For groupoids, for example, we can construct them from topological spaces, and there's more in the topological space than in the fundamental groupoid. And as a last example, I will give the colimit of a diagram of sets, for example, and where the extra data is the whole diagram. So I'm going to list a number of situations and then comment them further. The situation where we have more than we asked for. the first situation I have in mind is deformation cohomology. So perhaps I should explain what I mean by that. That if I have an algebraic structure, for example, say an associative algebra, and I want to deform the structure of this associative algebra, the underlying vector space being fixed, then I have the notion of Rothschild cohomology. And there's a number of other situations of this, a number of other examples of this situation. So first of all, I can use other structure, the algebras, commutative algebras, and I have other kind of cohomology. I can deform I have a situation where I can deform a point in the manifold, and this is called, so there's a cohomology that appears which is called the tangent complex, or the cotangent, that depends if we want to, which way we want to look at it. If I want to deform a manifold, there's the so-called tangent cohomology, which is the cohomology of the tangent sheaf. So why do I say that we have more when we ask than we asked for? It's because if I look at the problem of deforming something, I'm just expecting a space classifying all deformations. But in all those examples, we get much more. We have a full complex. And the deformations are just classified by a tiny bit of this complex, meaning one homology group, or perhaps a truncation of this complex, if you want to enhance the deformation problem. So the question is, why do we have this extra structure? I mean, what is going on here? Can we interpret this extra structure? Let me give more example. So this is an example I like a lot. It's the Doyer-Kahn construction of localization of a category. So if I have C a category, W a class of arrows, I can construct, or at least I can try to construct the localization. And there's an actual description of this construction. And this construction factors through an object of a different nature. It's not a category. If you construct exactly this localization, at some point you get a simplicially enriched category. But we didn't ask for anything simplicial. We just had a problem concerning actual categories. So what is the meaning of this? So sorry, here, let me get the punchline, chain complexes. Instead of vector spaces, here we have a simplicial enhancement. In Galois theory, so if I look at Galois theory for polynomials, the problem is essentially to factor a polynomial P in factors of degree 1. And now, when solving this problem, we get a group acting on something, but we didn't ask for any group acting on something. So we get groups and torsors from a problem that didn't look like it necessitates groups and torsors. I guess I can briefly mention CZG also. And maybe a last example. Okay, maybe let me remove CCGs. I won't talk about them. Let me mention the fiber of a differentiable map. Which can have singularities. And this is also something we didn't ask for. I mean, I have two manifolds. These are smooth objects. I have a differentiable map between manifolds. This is smooth data. And somehow from this data, I can extract something that is not a manifold because it has a singularity. And let me finish. Do you have another? There's a third kind of situation where we have ad hoc constructions. This is, for example, the definition of cocycles via atlases. Another example is Serre intersection formula. So let me finish the list. The construction of the so-called derived functors. I can mention virtual fundamental classes. And I'll stop here. So what those situations have in common is that somehow they go a bit beyond the theory that they are used in. So the definition of a cocycle, it's a kind of map between two things, but it's not a map of manifolds. So something bizarre is going on here. And I guess everybody here, when they learn the definition of a cocycle, did ask, what is this thing? I mean, it's a bizarre thing that is defined on an open cover, and on intersection I have a data, but I have nothing on the covers itself, etc. So something bizarre is going on here. The formula of computing the multiplicity of intersection given by Serre is also something that is not at all justified by a classical commutative algebra. The construction of the derived functor is, I guess, is mysterious. I guess everybody here has asked at one time, why do we need resolutions? What is going on with those resolutions? And the definition of virtual fundamental classes also, it's completely an ad hoc definition to get the invariant that works, but we don't know why this is the one that works. This is not justified by the definition. So what I claim is that in all those situations, there's something of the same kind going on. And it's possible to understand the oddities of those situations if we change a bit the context. So the philosophy behind that is commonly referred to as derivation. So maybe that. So behind all the situation, I claim that there is something that is commonly called derivation in the homotypical sense. So this is what I want to try to explain now. So first of all, maybe let me mention what the consequences of all this are. So the fact that modules, to manipulate them, we need a basis and we need generators and relations. This led to the enhancement of modules in chain complexes. The same situation for any kind of structure led to the idea that classically, as an algebraic structure, it has an underlying set, and but we can have a situation where instead of an underlying set, we have an underlying groupoid, and so this is the main idea that I want to arrive at, underlying groupoid instead of sets. So I'll come back on this idea later. So for manifolds also, if I try to enhance the notion of manifolds so that I have so that to take care about the atlases, it's a bit a rough conclusion, but I arrived to the notion of stack. And here, if I try to enhance the notion of groupoids, taking care about some of the extra data that I have here, I arrived at the notion of infinity groupoids. If I'm trying to enhance the colimit of a diagram of set, which is a particular case of a quotient by an equivalence relation, and if I want to keep track of the diagram, so maybe I will say a bit more about this example. Let's assume let's assume I have the following diagram of set, and I want to compute the co-equalizer of this diagram. So in my head, I have the following picture for this diagram. I have an object C, and I have two objects A and B that are self-relations of C with itself. And I want to compute the colimit. So classically, there's nothing to do. The colimit is a single point. If I take the co-equalizer of this diagram, this will be a set with a single point. But if I want to remember that I had two ways to identify C with itself, then I can define another kind of colimit, which is the notion of homotopy colimit. Sorry, give me a minute. Okay, excuse me, I'm going to change my diagram to have a simpler I should have written what I have in mind. Sorry, so this is the diagram I have in mind, and so if I want to write it as an actual diagram, this is, I have C, A, B, C, D, and I'm sending it to the set with two elements AB. And so these are the source and target of these arrows. And so the classical colimit is a single point, meaning I had 2 points and I'm having relations between them, and so I identify those 2 points. And there's the homotopy colimit, which says that instead of, so here I will try to remember something about the multiplicity of identification between my 2 points. And so the idea is that I had 2 relations between those points, and so I will transform those relations into intervals, and I will obtain something like this. So this is a circle. And so from this data, I can generate a circle. And this is what is called the homotopy colimit. And the fact that the classical colimit is a single point is because the circle has a single connected component. So I can go back here. By connected component. So what I'm trying to sketch here, and I apologize if this is sketchy, is that, where is the pen? It's possible to from a diagram of sets, it's possible to build something more than a set, which is a space defined up to homotopy. And this is the same thing as the notion of infinity groupoids that I mentioned before. So if I want to use this structure also, if I want to enhance the classical situation to take care about the extra structure that I have in those situations, let me tell you what I need. So roughly, to take care about all those situations, I need what is called derived geometry. And meaning there is a context where the problem of deformation has exactly as an answer a complex and not a single vector space. Here, if I want to understand this bizarre localization of Dwyer and Kahn, I need the theory of infinity categories. And they can be thought as a category enriched on infinity groupoids. Or maybe let me say that what is derived geometry? Roughly, it's it can be modeled on spaces having an underlying groupoid of points plus a structure sheaf having also an underlying groupoid instead of just a set. So if you want some detail about the situation, ask me after the talk. I'm just trying to sketch a big picture here. And for Galois theory, if I want to understand this, I need homotopy types, for example. All right, infinity groupoids. And to take care about the singularities of the fiber of a differentiable map, this is also a situation where I need derived geometry. So I'm sorry I don't have the time to explain more in detail what this is. To take care of the definition of co-cycles, where the theory of stacks, well, let me say that stacks, they can be understood, as I said here, as spaces that instead of having an underlying set of points, they have an underlying groupoid of points. Set intersection, this is a feature of derived geometry. The construction of derived functor, this is a feature of infinity category theory. And virtual fundamental classes, this is also a feature of the so-called derived geometry. So there's a lot of derivation here going on. So let me try to sum up the principle behind all this. Derivation can be understood as replacing sets by groupoids and even the so-called infinity groupoids that I don't want to mention too much because I don't want to define them. So the idea that all the math that I could do using sets, I can do them again using groupoids instead of sets. So let me give a small table. So if I have construction based on sets, for example, like a group, the construction corresponding with groupoid will be a loop group, meaning the space of loop of a topological space. If I have a vector space, the analog in the world of groupoids will be a chain complex. If I have a topological space, the analog in the world of groupoid will be a topos or a stack, and etc. The list can continue. So let me try to argue for this. What is going on classically? I mean, we had system of linear equations, for example, and then we constructed the notion of a module to encompass the structure of the solution of this. So by doing so, what is kind of the what is the definition of a module? It's an equivalence class of a system of linear equations that I have generators and relations, and I can understand my modules exist because I can have generators and relation for them. And but if I write a presentation of an A module over some ring by some generators and some relations, I have more here. And somehow, if I look at this data as a chain complex, M is only the zero cohomology of this complex. So this is a choice that from this data I will remember only this part of the data, meaning I will remember only the quotient of this map. But there's another choice that can be made. Sorry, define. So I don't claim this is the only way to define mathematical object, but this is definitely one way, is to have a bunch of data that generates something, and we can define mathematical objects by equivalence classes of generating data. And so this is a very interesting philosophy. It's so those generating data if I'm thinking that they generate objects, they live in some categories. Say a category C. And now I want to define an equivalence relation on those generating data. This leads to distinguish some particular arrows in C that are called usually weak equivalences. So this philosophy that I'm trying to sketch here is what is called the philosophy of model. There's a number of situations in mathematics of the following kind. The object that I'm interested in is defined as an equivalence class of some structure. This is my generating data, and classically these are called models for the object that I really want to deal with. And so the category of interest will be defined technically as starting with the category C, distinguishing some arrows W, and I really want to pretend that W's are isomorphism. So there's a construction that does the job. This is called the localization. And we can, so I claim that all the situations, so for example here, we can define a module by equivalence classes of a system of linear equations. We can define a manifold as an equivalence classes of atlases. We can define a groupoid, even if it's a little bit twisted, as an equivalence class of topological spaces. Okay, I won't say more. And And this is a fact that there are several choices for W. So I mentioned, for example, that if I have a presentation of modules, and if I have two presentations of the same module, I can define a morphism of presentation as a commutative diagram like this. So this is how the generating data do form categories. And then I have an equivalence relation between those two guys by saying that if I think of them as complexes, they need to, so this map of generating data needs to induce an isomorphism at the level of the H0. So let me give you another example to be clear. If I have two topological spaces, I can define a map to be an equivalence if the induced map between the connected component is a bijection. This is a reasonable notion of an equivalence. It's probably the most stupid way to define sets, starting with topological spaces. And so historically, this is kind of the first idea that people had. They had a bunch of structure generating other data, and they truncated a lot of the generating structure to extract what is generated. So in the situation, we look only at H0 and pi0, but we know because of experience that I have more than H0 in a complex. I have all the Hi. And in a space, I have higher homotopy invariance. And so I can change my notion of identification, which is to change W. And I could, for example, ask for a map of generating data for modules to be an equivalence if not only the H0 are the same, but all the Hi of my complex are the same. And I can define for a map between topological spaces to be an equivalence if not only the connected components are the same, but every homotopy invariant are the same. And this is the idea behind derivation, is that we had a kind of crude way to identify some structures, and we relax this identification a bit so that we have extra structure that depends on our generating data. And the purpose of this is so that the objects of study are more regular. So this is not something that I will have time to explain very much, but if we change this definition of objects, then suddenly the property of objects become nicer. Let me maybe give an example, that if we work in the context of chain complexes, for example, it's natural for the deformation of an associative algebra, which has an underlying chain complex, to be itself a chain complex.
What is the difference with infinity groupoid?
So I'm claiming that the chain complex is an infinity groupoid with a structure of an abelian group. There would be something to say because somehow infinity groupoid they correspond to bounded chain complex, to say in positive homological degree, and we can have unbounded chain complex. So we can go a bit beyond infinity groupoid if we want, but I don't want to enter this. Maybe my time is up. So okay, let me make a remark in conclusion. So this philosophy of models, and which are so there's several axiomatization to deal with those constructions. It's very hard in practice to compute the localization of category, and we need some extra structure on C and on W to be able to work with those guys. And so, for example, we have calculus of fraction, or Couldon model structures, etc. But this philosophy is very powerful, and it's quite enlightening to revisit very classical mathematics, even the construction of modules from this philosophy of having some generators and relations, and or some fancy variation on such, and we're trying to produce something from that, but we somehow we went too fast into the object that we wanted to study, because we assumed that from this data we want to produce an object having only an underlying set, meaning some set with some structure. But the better notion of object is an object that has more than just a set as an underlying structure. So we can imagine a refoundation of mathematics where instead of starting with sets, we can start with groupoids. So this is what Eric will talk about in the next talk. I confess I'm a bit skeptical on this approach. Not that I think it's not interesting at all, but I think this philosophy of having models and generating object of interest as equivalence classes of models, it's very important, and it's very natural. So if we start to do math, just replacing sets by groupoids, somehow we will miss a bit of the philosophy behind models. This is my personal opinion, that sets are very fundamental for the intuition in mathematics. And even though groupoids are very nice to explain a lot of phenomena that is going on, I think sets will still be an important part of the approach of mathematics. But I guess that's for a debate after Eric's talk. Okay, I'm going to stop here. Thank you very much.
Could you clarify a bit what you meant with the Galois theory example?
Oh,
I should think about it.
So Galois theory for me is, I guess it's the first example of a torsor that I learned. It's if you wanna factor a polynomial in factors of degree 1, then this factorization is not unique. So this is where there's an ambiguity that appears, and there's a universal solution. So you can start with a ring of coefficients, and you add formally variables that will be the roots of the polynomial, so you force them to be the root of the polynomial. This is the universal setting where you have a canonical factorization of your polynomial. But in this setting, the factorization is not canonical in general. And so of course you can permute the variable, and this is one source of non-unicity of the factorization, but there's more. In general, the number of factorization, when you add formally all the roots, the action of the permutation is not transitive on them. And so this is what Galois theory is doing, that it says that, oh, this object that was canonical to solve our problem, we can forget about it, and we can follow smaller objects, where we can master the ambiguity, and the ambiguity will reduce to some permutation to the action of some group of permutation on the roots. And so the way I see Galois theory, it's more like a theory of reduction of ambiguity. Because we start with a universal problem, and somehow we don't control all the different choices of solution, and so but by finding a smaller ring of coefficients, we can completely control the factorization. And then there's more in Galois theory than just this aspect. I mean, there's the fact that knowing the structure of the group, I can construct my extension of rings and blah blah blah.
Yeah, the basic notion of torsor is a space on which a group acts transitively. So in that case, it looks like the torsor is a way of producing ambiguity, like you lose track of the distinguished neutral element of the group when you shift to the space on which it acts. So, but you claim that torsors were a way of reducing ambiguity, not...
No. So for Galois theory, what I say that I start with a sigma n torsor, and I construct a sub-torsor. So a torsor on a smaller group. And this is Galois theorem that says that if I have a function of the roots of a polynomial, then it is rational if and only if it is invariant under the action of a subgroup of sigma n. So this is in the sense that I reduce the ambiguity because I have a big torsor and I construct a sub-torsor.
Yes?
I would like also to mention that, first of all, the definition of a groupoid as a category, etc., is slightly misleading. It's correct, of course, but it's slightly misleading. For me, the groupoid is a geometric object. And of course, when Erosman introduced groupoid, a Lie groupoid, it was with differential geometry in mind. And so the small point is that when you depict a category like that, you look at the set of objects and the set of arrows to be discrete, without any distraction.
Yes.
Of course, what is really interesting is an enriched category. And for instance, a Lie groupoid is not only a collection of objects somewhere on the table, it's a manifold, and the objects are the points of a manifold, etc. So I like to mention that well, first another point also, which is of course very tentative, is that it seems that so far no one has tried to introduce groupoid in the genomics.
Sorry?
In genomics.
In genomics?
Yes.
Okay. What do you mean by that?
But I mean that, of course, when you have a chain of DNA, it's a very, very long chain. But it has regularity and structure. But these are local regularities. That means you don't have a global pattern. So many components that you don't have a global. But you can, and you have a chain, and this piece can be very similar to that piece, and they can interact. That's the way. That's the way it interacts.
Yeah. Okay.
Through chemical compounds, but so it seems that it's possible. It would be possible to model. I mean, it would be possible to model DNA by groupoid. Groupoid being a description of a local symmetry, not a global.
Yeah.
If you consider that the groupoid expressed in differential geometry, a local symmetry, not a global symmetry, which is of course what you have engaged here in those things in physics, then you come to something interesting. But of course, no one has done that for the moment, as far as I know. But it would be, and also what is interesting is that if you apply the method of Erosman for Lie groupoid, you have differential equations which are connected. That means Lie groupoid are Lie groups. That means they have something which is the Lie algebra, which corresponds to the Lie algebra of a group. And so that makes an algebrization of this geometrical situation. And so you have differential equation, and that would be one of the key to understand the genome. One key.
That'd be great.
Yes. But I'm just making a suggestion. I know too little about genomics to be serious about that, but I think that there's something there.
So maybe I can add a remark to your comment. I think there's two ways to think groupoids, and they're reflected into the definition of Erasman and the definition of MacLean of a category. So we can think a groupoid as a kind of category, or maybe the fundamental groupoid of a space, meaning really some point connected by some path. Or we can think of it as action of local groups that don't compose, and this was Erasman's point of view. I think there's a difference between the 2 points of view in the sense that in the first point of view, it's kind of natural to look at groupoids up to equivalences of groupoids, whereas in the Erasman point of view, we don't want to look at them up to equivalences.
Because if
Well, except that in leaf spaces, when you want to define leaf spaces, which is a kind of equivalence.
Yes, yes.
And there, of course, that's a good example where we have an equivalence relation, 2 points of the manifold are in the same leaf, or let's say you have a dynamical system like on the same trajectory, the same path. But of course, the quotient is complicated. The natural quotient is set theory completely useless.
Yeah.
And the philosophy to me is that instead of going to go to the quotient, you keep, well, that's what you explained, you keep the scaffold behind it, you keep the scaffold behind it. And so, but then, of course, you need, and I think that's exactly what you explained with localizing the category. And for Groupoid also, you have the notion, natural notion of Morita equivalence for Groupoid, which is exactly what we have. And so, and in a sense, a Groupoid up to Morita equivalence is more or less the space we are looking for.
Yes. Yeah, that's Morita equivalences are just a way to compute morphisms here.
Exactly.
Yes, yes. Yes, Gabriel?
In a sense, we could say that in physics, people discover a part of this without knowing anything of derived geometry. In the engaged theories, if you want to obtain the functions on the symplectic quotient, you can do it as you can define the observables, the so-called observables, as the zero-degree cohomology of a complex. But when you do so, there is a problem, which is that you obtain the whole cohomology at all levels. No, and in general, it's not very clear what to do with these higher cohomologies.
Yeah.
So, do you think that the people who developed this didn't know again anything about derived geometry? So, do you think that this kind of derived philosophy can provide any kind of insight on the physical significance of these higher cohomologies in engaged theories?
That's a good question. I mean, all of this was discovered by practice and not at all by some a priori principles. Actually, the a priori principle was the reason of, let me call that a misleading thing, that from generating data, I truncate too much the generating data and I build this. This was because there was implicitly the paradigm of set theory. If we relax this paradigm into having a groupoid instead of sets, then we get something more. But mathematicians have been convinced by that by practice, because they had those bizarre constructions that I listed here, and they needed to understand them. I mean, what is the structure the extra structure that we have here? And so I guess the history in physics and in mathematics has been the same. I mean, people have computed things and they have found chain complexes, but they were interested only in a small part of the chain complex that they could understand and interpret. Now, it'd be fantastic if the insight of derived geometry would give an interpretation, a physical interpretation of the whole chain complex or something. I don't know if we're yet there, but I hope somebody, I guess Urs is going into this direction. Because the use of stacks, maybe not so much the so-called derived geometry, but at least the use of stacks, it's one way to say that we have extra structure and it's part of the object. Maybe let me mention one thing, that the notion of a co-cycle, this is something that I like very much. That's if I have a manifold X and I want to understand a co-cycle with value in a group G, then a co-cycle is something as an actual map between geometrical objects, where this is a manifold and this is a stack. So this is just a new kind of manifold. This is an extension of manifolds that we need, so that co-cycles that were bizarre data depending on an atlas and that we had to work up to equivalence become an actual object. And this is already useful in physics, because some fields in physics are exactly co-cycles. Some fields are functions with value in a manifold, and some fields, like the data of a connection up to gauge equivalence, they are exactly co-cycles, and they take values in stacks instead of spaces. So I guess that's the beginning of an answer for your question. Yeah.
Maybe we can go on with the coffee.
Last question?
Last
maybe?
question.
Just about what you said. So could you comment a little more on the difference of nature between homology and homotopy in these theories?
So there's there's a lot of things to be said. Let me suggest one thing, that if I start with topological spaces, I have the homotopy theory of topological spaces, and I have the homology, say, with coefficient in Z. And the homology is, in a precise sense, the Abelianization of the homotopy. And so I don't know if this is the kind of answer you were expecting, but...
Not exactly.
Ah, okay. Sorry. I guess you knew that. So maybe we can discuss more after that.
Just last remark about BG, because you mentioned BG. Of course, the natural definition of BG is what? You have a group which acts G, which acts on the point,
Yeah.
and you take the quotient of the point by the
Exactly. That's beautiful. Actually,
exactly the definition of a Borel. If you work up to
Yes.
homotopy, a point is equivalent to a point, to a contractible space. You let the group operate freely on the contractible space. You take the group.
Yeah, yeah.
That's exactly the definition.
Exactly. That's beautiful. This is something I tried to explain with my notion of homotopy limit, but I guess I was I don't think I did a good job with that. But actually, conceptually, the most important notion behind all this is this notion of homotopy limit, and it all comes to that in the end. So this is something I didn't have time to elaborate, but this is definitely the most important notion behind that.
But if you ask Alan Cohen, what is BG, he would say, the C-star algebra.
Well, yeah.
We explained everything in terms of non-commutative.
Yes, but at least he's looking at it up to Morita equivalence, so that's good.
Yeah. Yes, of course.
So maybe we can stop for some minutes. There is a coffee in the somewhere outside. So.
Yeah. Okay. Thank you very much.